Gas detectors, ionization chamber and grid ionization chamber. So mainly gas-filled ionization detectors are nuclear radiation detectors, and how they function is they generate an electric sign which is out of the ionization, and the ionization is produced in the gas by the interaction of the gas with the coming radiation. And there are mainly three types of detectors, that are ionization chamber, proportional counter and GM tubes. And these three has a common feature, that the sensitive volume of the gas that is subjected to an electrostatic field, and this electrostatic field is generated by giving a suitable voltage difference between the two electrodes. The two electrodes are placed in a gas, and the strength of the electric field and the pressure of the gas, these two determines the detector response to the ionizing radiation. So we can see the diagram of a gas filled detector. It consists of an anode, cathode, insulator, and this PA stands for pre-amplifier, and then amplifier, from the where we will get the signal. And here the wall of the ionization chamber will serve as the cathode, and a thin wire is placed along its axis which act as the anode. Now the positive voltage is applied to the central electrode, so that the electrons that produced will move towards the anode. And the electric field that we apply is very small, so the electrons will lost by a recombination effect. We can see that in the graph there is a region A, B, C, D and E, and the region marked as A, that is not useful for the operation of the detectors, and the region B, here the recombination of the negative ions and positive ions is negligible. So therefore the number of electrons which reaching the central electrode will become almost equal to the electrons that are produced. And the region, therefore this region will give the range of operating voltage for the chamber. And ionization chamber is used for detection of heavy ionizing nuclear particles. Here the region C, proportionality, and in region D there is only limited proportionality region, and the other one is the GM region. Now we come to ionization chamber. Ionization chamber mainly functions by generating an electric signal out of the initial ionization, which is directly produced in the gas of chamber by the interaction of radiation. Now here we apply voltage difference between the two electrodes. Therefore the sensitive volume of the detector gas is produced and maintained in the electrostatic field. Here the negative and positive charges will separate, and it will causes the production of the induced current. So therefore the pulse height analysis, that is a graph to measure the energy deposited in the volume of the gas by the nuclear radiation. Now we can see that an ionization current can be operated in two modes, that are either in a pulse mode or in direct current mode. So therefore the in direct current mode, the average current through the external circuit is measured to determine the mean intensity of the radiation. Okay, now we can see that a parallel plate ionization chamber. Parallel plate ionization chamber mainly consists of two parallel plates that are separated by a distance and are enclosed in a gas filled chamber. Also the ionization chamber has parallel plate geometry as well as the cylindrical geometry. These two are the most commonly used. And in parallel plate, the volume that are enclosed by the two plates that is in the that are kept at a potential difference, and that is the sensitive volume of the chamber. Now it is direct current mode operated ionization chamber, and in this operation the chamber is operated to measure the average current due to the motion of negative and positive charges that are produced by the radiation. Here for the fixed intensity of an incident ionizing radiation, the current in the chamber will initially increase with increase in the applied anode voltage, and finally it will reaches a saturation value. And so therefore the applied voltage should ensure that the chamber is operating in the saturation current region, and there will occur a small current loss due to the diffusion of the charge carriers, and this current loss will decreases with the applied voltage, and it can be minimized by choosing a resistor which is high value of the applied voltage. Now it is guard rings. We apply voltage between the two electrodes, and when we apply voltage, a direct current will flow across the leakage resistance of the insulator, which is to electrically separate the two electrodes. For separating, we place insulator, and the effect of leakage current across insulator is minimized by providing a guard ring in an ionization chamber. We can see the diagram of the usage of guard ring in a cylindrical ionization chamber. Mainly guard rings means these are the conductors which divide the insulator into three parts, and when guard rings are provided on the chamber, most of the leakage current which is across the insulator will does not pass through the device measuring the ionizing current. Okay, next is the ionization current measurements. There are mainly three methods for the measurement of the ionization current. The first one is the use of electrometer, and the electrometer will measure the voltage drop which is across a very high valued resistor that is placed in the measuring circuit. And the second method, the ion current signal, it is converted from DC to AC, and then it is getting amplified. So this conversion from DC to AC is done by collecting the ion current across an RC circuit in which the capacitance C is sinusoidal. Here one measures only the integrated ionization current over a period of time. When C is a capacitor across the ionizing chamber, and when it is initially charged to a voltage VB, then the voltage sources resolve. So if the total ionizing charge is Q0, then the voltage change across the capacitor is dVB equal to Q0 by C. Next is a measurement with direct current ion chamber. It directly measures the exposure by measuring the ionization of all secondary electrons. That is free air chamber for the low energy radiation and cavity chamber for high energy radiation. Then Bragg-Gray principle is mainly used to determine the absorbed radiation dose in the given material. Next, we have discussed direct current mode operation. Next is pulse mode operation. We can see the schematic diagram of a parallel plate ionization chamber. It consists of anode, cathode, insulator, guard ring, the chamber capacitance, etc. Here the electric field is applied between the electrodes, and that determines the volume of the chamber. Charge carriers will result in the induced current in the external circuit. In an electron collection parallel plate ionization chamber, the output charge signal mainly depends on both the deposited energy and location of ionization. Okay. Now we determine the pulse formation in parallel plate ionization chamber. Here the two plates are separated by D, and the cathode is at voltage minus VB, and anode is grounded through resistor R. Guard rings are there, and the energy stored is equal to Q2 by 2C, and Q square by 2C. And now we are going to deduce the expression for the time development of output pulse due to the motion of n electron ion pairs formed at a distance x from the cathode. So the rate dE by dt of the energy gained by the electrons is given by dE by dt equal to NEx dx by dt equals minus NE dV by dx into dx by dt, where V is the potential and x is the electric field at the point x. This energy is derived from the electrostatic energy stored in the condenser. So d epsilon by dt equal to d by dt. We are substituting for E, that's q square by 2c. So we will get that's equal to V into I. I means the current that is flowing in the external circuit, and so from these two equations we will get that the current I is equal to minus NE by VB dV by dt, where dV by dt is the rate of change of the potential. Okay. um, now we are considering the case where the time constant RC is much larger than both the electron collection time and ion collection time, and so the induced charge due to the motion of electrons means Qt equal to minus NeVet divided by T, where Te is the electron collection time is given by D minus X by VE. So the induced charge due to the motion of positive ions is Q, positive ions, therefore Q plus T equal to Ne Vt T by T, and where the positive ion collection time is given by X divided by Vi. So therefore we will get the induced charge at the anode is equal to Qt, Q minus of Te plus Q plus of Te, and so we can the distance moved by the ion during the electron collection time Te is negligibly small, so that is therefore the maximum of charge pulse reached during the electron collection is given by Qt equal to minus Ne by D into D minus X, where both the electrons and ions are collected. Charge pulse reaches a maximum value which is given by minus of Ne, and the maximum pulse height is Vmax equal to minus Ne by C. And here we can see a graph which is the value of the output voltage V0. Output is V0, which is resulting from the collection of both electrons. We collect both electrons and ions, and its graph is being shown for the typical values of X, D by 4, D by 2 and 3 D by 4. Okay. Therefore, in grid ionization chamber, the electron collection pulse height becomes independent of the position of ionizing, making it suitable for energy measurement. Now, this is the diagram of the grid ionization chamber, where K is the cathode, this is the grid, and C is the collector, and there is also guard ring. In parallel plates, the containing grid wire is placed between cathode and anode, and the cathode is cathode and grid are at negative potentials of minus Vb and minus GVb. Okay, and now the anode is grounded through the resistance R, and guard ring is also placed around anode. Now the chamber is filled with purified noble gas mixture and at pressure which is sufficient to ensure that the charged particle is range of the charged particle is less than the distance between grid and cathode. Now the shielding effect of grid and the collection of electrons by the grid wires has to be minimized. The shielding defect in this it is determines the extent to which the grid wires failed to shield the collector electrode from electric field in the ionizing region. Now the conditions that to avoid the electron capture by the grid wires is given by x2 by x1 should be greater than or equal to 1 plus rho plus 2 L rho by d1 by 1 minus rho minus 2 L rho by d1, where x1 and x2 are the electric fields in the grid cathode and grid collector regions, and rho equal to 2 pi r0 by d0, L equal to d0 by 2 pi into rho square by 4 minus lnp. R0 means the radius of the grid wire, and d0 is the separation distance between the adjacent grid wires, and d1 is the grid cathode distance. So therefore x2 by x1 greater than or equal to 1 plus rho by 1 minus rho. The shielding defect sigma 0 is calculated. Sigma 0 equal to d0 by 2 pi d1 ln of d0 by 2 pi into r0. Now in grid ionization chamber, the energy measurements. So for monoenergetic particles, the standard deviation of the output pulse height distribution of the can be written as sigma square equal to sigma I square, sigma t square, sigma ch square, and sigma l square, and these are the contributions which are arising from the statistics of ionizing process, target thickness effects, and electron losses, and shielding defect of grid and electronics. So we can see here back to back grid ionization chamber. Okay. Now in grit ionization chamber, mainly the alpha particle and fission fragment energy measurements involve a source placed at the center of the cathode of chamber, and this causes the pulse height spread due to the variation in the source foil thickness and energy loss in the target foil. So for minimizing this causes, the source should be thin and uniform. In some cases, we use a grid ionization chamber for heavy ions that have a thin and uniform window, and the proper design and operating conditions will minimize the contribution of our sigma CH. Okay, to minimize electron attachment, the fill gas should be purified, and it should be continuously purified, and for fission fragments and heavy ions should be used. Now the electronic contribution can be minimized by reducing pre-amplifier noise and selecting appropriate shaping time constants. So alpha particle energy resolutions can be improved to about 35 k electron volt by giving electronic collimation. Now a grit ionization chamber means it is basically a device which is mainly used to measure the energy and the track angle of the fission fragments, and it acts as a parallel plate chamber within the pulse formed at the cathode, or the grid that affecting the energy of the charged particle and its trajectory with respect to the electric field direction. So the pulse height at the collector depends on the particle energy, and therefore the measurement of both the energy and angle of particle track with the electric field direction it allow. Now the back-to-back grid ionization chamber, which we have seen in the diagram, is used to study the fission process. Okay, so the back-to-back ionization chamber was used to measure the angle of emergence of the fission fragments that are emitted from the small area at the center of the cathode in thermal neutron-induced fission of uranium-235 as an example. So this back-to-back grid ionization chamber mainly provides a useful device for measuring energy and angle of the charged particles that are emitted at the center of the cathode with almost 100% efficiency, and therefore it is making us a powerful tool for measurements involving very low probability events. Thank you.